Today I'm going to talk about the dispersion relation of electromagnetic waves in plasma without magnetic field, that is B naught equals 0. And here you can see the dispersion relation of the electromagnetic waves is modified by this term. In the absence of this term, we have omega square equals C square K square, which is the dispersion relation of electromagnetic waves in vacuum. Now we are going to calculate the phase velocity of the waves of the electromagnetic waves in plasma. From here you can see, we can easily write it down like that. If I make a slight readjustment of these terms, and now I can write it in this form: omega square over K square So here you can see that this term is going to be greater than 1. As you can see, 1 divided by something which is less than 1. As this term is in square, so we are always expecting a positive value here. So 1 divided by something less than 1 will give you a value greater than 1. So here you can see that with phase velocity square is going to be greater than c square. But if I calculate the group velocity of for this expression, then it always comes to be less than c. As I've already told you, the phase velocity doesn't carry any information. The information is carried by the modulation of the wave, which is given by the group velocity. So there is no harm in looking at this expression that V phi is greater than c. Now let's look at the group velocity. This is going to be d omega by dk. So if I differentiate this term, 2 omega d omega by dk equals c square k square. Oh, sorry. 2c square k. I have to drive it with respect to k. So from here I can see d omega by dk will be c square divided by omega by k. Now this is the phase velocity. Now if I'm going to divide c square grid with something which is greater than c, I'm going to get Vg less than c. So it shows us that our expression is correct. There's no violation of any law here. That the group velocity comes out to be less than c. Now if I want to plot this term, omega square equals omega p square plus c square k square. As you remember, we have encountered this kind of expression in electrostatic waves, that is with the electron plasma waves, which was omega square equals omega p square plus k square v thermal square. Now this is the expression for the electron plasma waves, and we have already plotted this term, but the difference is here is the thermal velocity, and here is the speed of light. Now if I plot this expression, I get the same plot as in the case of the electron plasma waves. here the asymptotic value, it turns out to be C, and this will be omega P, and I am plotting here omega versus K. So this is a graph of this equation. Now, if I want to, I'm going to show you a bit more about this relation, why it is so important. You can see I can write it in this form: C square K square equals omega square minus omega P square. Now, from this expression, you can see that if omega is greater than omega P, then we have C square K square greater than 0. If omega equals omega P, this C square K square equals 0. And if omega is less than omega P, then C square K square will become a negative value. Now, these three situations represent three different scenarios. If the incoming frequency of the electromagnetic waves that is going to interact with the plasma has a frequency greater than the plasma frequency, then the wave will propagate. If the incoming frequency of the wave is equal to the plasma frequency, there will be no propagation and the wave will be absorbed. Now, if omega is less than omega p, means that if the frequency of the incoming electromagnetic wave is less than the plasma frequency, this k square becomes negative. And if k square becomes negative, that means that the propagation vector k becomes a complex quantity, which shows us the attenuation of the wave. I'm going to show you in a minute, but just analyze it in a different way. Let's consider a case that we have a plasma created in a certain lab, and then we want to find out the density of the plasma inside. Now, this case is we can use this kind of analogy to get the density of the plasma. How you can do that? That we start giving electromagnetic waves with a certain frequency to this plasma. When the frequency and we start off with a high value, or we start off with a low value, and all these waves will get reflected back because of this case, that k square will be negative and no wave will propagate through plasma. When omega becomes equals to the plasma frequency, we will get nothing out, and when the omega is greater than omega p, we will get a signal out at the output. So this is how you can find out the density of the plasma, because in omega p we have all the other terms are constant, n naught e squared by epsilon naught m. So we have the charge of the electrons, we have epsilon naught, we have the mass of the electrons. So this term we are going to find out if the incoming frequency of the wave becomes matchable to the plasma frequency. So this is an experimental setup where we can find out the density of the plasma that has been created in certain lab environment. This situation, which is called omega equals omega p, we call this a cutoff. Means k equals 0. There will be no propagation of the wave, and we can find out the densities I already told you. Now, if you can see that if omega is less than omega p, then Ck will be, now you can see that if omega is less than omega p, we are going to have an iota here. Now you can see that now k is imaginary. As you know that we have this the perturbed quantities all have this kind of E1 or B1, all goes like that, exponential iota kx minus omega t. Now if this k it has an imaginary part, then we are going to have an attenuated term. I will write it like that, iota k real plus iota k imaginary into x. Then you can see that this imaginary part will give us the damping of the wave. So this is how you can see that if omega is less than omega p, the wave is going to get damped inside the plasma and it will not propagate. And the most for most of the plasma environments that we studied in the lab, the cutoff frequency lies in the microwave range. This omega equals omega b that I'm talking about. Now we can find out. Okay, now I'm going to analyze this expression in a different way. Now I'm talking about the refractive index, which is the speed of light in vacuum divided by the speed of, or you can say, the speed of the electromagnetic wave in vacuum divided by the speed of the electromagnetic wave in that medium. For plasma, as we have already seen, that by using this equation, I can write it c square k square by omega square equals 1 minus omega p square by omega square. And from here I can easily show to you omega square by k square equals 1 minus p square by omega square. And from here I can write c square by v phi square 1 minus omega p square by omega square. So, and I can write it like that. So here you can see that the refractive index turns out to be less than 1. In usual medium, this refractive index is greater than 1, as the speed of light in that medium turns out to be less than the velocity or the speed of light in vacuum. So, so it's a for this kind of situation, there is an interesting fact that if you make a convex lens that is made of plasma, that instead of converging the light, it starts diverging the light, which is an interesting phenomenon. So this is the consequence of having the refractive index less than 1. Now I'm going to show you what will happen with these three conditions on the electromagnetic waves passing through plasma. That, how can we use these conditions and why these conditions are important to study. So let's consider a scenario where we are trying to communicate with the satellites that are circling around the plasma outside the ionosphere. So let's suppose this is Earth and we have a transmitter here which is sending certain electromagnetic waves in the, and this is the ionosphere of certain thickness, and we try to communicate with the satellite that is positioned somewhere here. Now, if we want to communicate with this satellite, we have to send a signal in this range. If the frequency of the signal is greater than the plasma frequency or the frequency of the plasma that exists in the ionosphere, then we can communicate with this satellite. Otherwise, these waves will reflect back according to this condition. Now, if we want to communicate with another tower or another uh, communication, or you want to communicate around the earth, then we will send a signal in this range, omega less than omega p, and it will get reflected back, and it will be cached by this another receiver. So the practical problem that exists with this kind of situation is that when a vehicle which is on a flight mission in space comes back to Earth and it enters the atmosphere, then the situation is a bit different from this one. Let's see. Let's suppose that this is the space shuttle that is coming back, and with the resistance with the air, it has created a plasma around it. Now, when we are trying to communicate with this re-entry vehicle, the plasma created here, we don't know about the density here. What kind of density has created here, and what kind of plasma is it? So, for a certain specific period of time, we can't communicate with this satellite because of this blockage, because the wave that we are sending might be less than omega p, and we get a reflection of this wave according to this condition. So when the vehicle re-enters into the Earth's atmosphere, we call it a blackout, but we don't know the exact location of the vehicle. And when it gets landed on the surface, or usually in the sea or something, then we can communicate with that. So this is an important thing that we have to consider when we are talking about the electromagnetic waves in plasma. Such kind of situations also occur when we are trying to communicate with the satellite. That, as I've already told you, that we have an ionosphere around, and this ionospheric density is basically dependent upon the activity going on the sun, that is the solar wind. So when the activity on the sun gets or the sun becomes more active, that means that the fission reactions and the fusion reactions get more and more on the surface of the sun. This solar wind, the density of the solar wind increases, and that solar wind, which is coming from the sun, increases the density of the plasma here. And by increasing this density, this omega p increases. As omega p increases, we don't know which kind of frequencies we are going to use to communicate with the satellite that is orbiting around the Earth. So that's a big problem in many strategic planning, as we don't know about the activity of the sun and when it's going to be when it's going to rise. So at that moment, there's also called a communication blackout. Communication blackout, and we cannot interact with our satellites that are orbiting around the Earth. This is a big problem for the advanced countries that are using these satellites for surveillance and other purposes. That if somebody is going to know about that at certain period of time, they don't have any information about certain location. So whatever is happening out there, they are not they don't have a clue about it. So it's an important thing that is related with these expression. which is the expression for the electromagnetic waves inside the